Okay, so yesterday we learned that in order for an object to be in motion, it has to have an unbalanced force applied to it. Or for an object in motion to come to stop, it needs an unbalanced force applied against it, because a force is either a push or a pull. We either push the car, i.e., we push on the gas pedal and it makes the engine turn over and gives us more power, and we accelerate, or we pull in that we pull the brakes on, we press on the pedal, the brake squeeze on the brake pad, the tire stops spinning. There's also the friction of the road against the asphalt. If we didn't apply the brakes, our vehicle will still come to a stop because there's friction working against it. So an unbalanced force will cause the mass to accelerate, and we will always see it in books written as acceleration is equal to force net divided by mass. But we also need to know that force net is equal to mass times acceleration. So that's the second law. An unbalanced force will cause an object to accelerate or decelerate. Newton's first law is that an object An object will remain at a constant velocity unless it's acted on by that unbalanced force. So it's basically taking the second one and retweaking the sentence. It's the law of inertia. Okay, it will stay at a constant velocity, and an object at rest, this is the famous saying, an object at rest will stay at rest unless it's acted on by an unbalanced force. Everybody's heard that. So the more mass an object has, the more inertia an object has. Because what did we learn yesterday about force net and its relationship to mass? Say it out loud. It's proportional, right? As mass increases, the force will increase. Okay, so this is the second law. This is the first law. Here's an example. When you ride in a car and driver slams on the brake, how many people have done this thinking that they'd be funny to their friends? Drive and you slam on the brakes and you watch what they do. What do? They go forwards, right? When you're driving a little itty bitty Fiat and you hit a deer, your body is still traveling at that speed when you hit the deer. Okay? The passenger is traveling in the same direction at the same velocity as the vehicle. The fact that a vehicle comes to a stop does not mean that the passenger comes to a stop. And so the greatest invention ever for driving is seatbelts. That seatbelt will act like whatever stopped your car, it will stop you. Okay? So if you're driving and you're wearing a seatbelt, the parts that are not restrained by the seatbelt still go forward, which is why people get whiplash in a car accident. Okay? Their head is still going forward, and then it comes back and it hits the seat. And so it's being forcibly stopped in one direction. Okay? What about when you go around a corner? What does it feel like when you go, say you're going on to the bridge and you're not reducing your speed? You're convinced you can get onto the bridge at 100 kilometers an hour. What does it feel like going around that corner? Okay? So when you go around a corner, This is the direction of motion, but inertia says that you are actually traveling in that direction. Okay, you lean your body because you actually still want to go in that initial direction. You're coming down the hill, you've got to make a sharp left-handed turn to get onto the bridge. Your body wants to keep going in that same direction that you were coming down off the hill. So eventually you would end up driving through that little graveyard, that house, Maples Garden, and out into the river if you kept that direct line coming off the hill. If you didn't turn the corner. And then once you turn the corner, you do your lean, the corner stops and your body rights itself and you're like, okay, now we're going in this direction. I'm going to go in this direction with my car. You come off the bridge and now you're leaning this way because your body wants to go straight up that hill, but your car, you've angled it to go around the corner. You've told the car, go this way with the steering wheel. Your body didn't get the message and it goes straight. Okay? So Newton's second law is what? Use your notes to help you out. Newton's second law is what? Right, an unbalanced force will cause a mass to accelerate or decelerate. What's Newton's first law? Right, an object will stay at a constant velocity unless an unbalanced force is applied against it. In English, an object in motion will stay in motion until it's acted upon. Or an object at rest will stay at rest until it's acted upon. When you guys were practicing your shoot for a marble, the marble didn't move until you let go of it. And because it was on an incline, there was gravity forcing it down. The force of gravity forced it down the ramp. And the force normal and the force friction. Okay, there has to be an unbalanced force applied in either direction. When we go back to the first notes, remember, if a force is applied in the same direction of motion, you have acceleration. And if the force applied is in the opposite direction of motion, you have deceleration. Let's look at the third law of motion. The third law of motion says that an object exerts a force on a second object. That second object will exert an equal and opposite force on the first object. So in English, for every action, there is an equal and opposite reaction. Okay? Forces always work in pairs. Always. There is no discrepancy on that. If I look at the first example, when a blown up balloon is released, the balloon accelerates forward as the air in the balloon escapes out the opposite direction. So if I was to look at the force of the balloon, what would be the opposite reaction? What would be the opposing force? the balloon is going one way, what's going the opposite way? The air. Why would I put the negative sign in there? What do negative signs tell us? Opposite. Negative signs tell us opposite. They're an indication of direction. If I was headed west and my answer came out to be negative, what direction am I going? East. If I was heading north and my opposite direction, my answer was negative, what would be my direction? South. Negative is a sense of direction. Okay? What about this one here? When a gun is used to shoot a bullet, the bullet goes off in one direction and the gun kicks back in the opposite direction. How would I write this out if I had to write out an equation statement? What would I say? What's moving in our unspoken positive direction? So if Newton's third law states that there's equal forces acting on each mass, why does the bullet accelerate much more than the actual gun in the opposite direction? So if I've got my gun and I fire a bullet, why does the bullet move faster away from the gun than the gun moves backwards on the recoil? The gun has more bounce, more mass. Sorry, I thought you said bounce. That's exactly it. The gun has more mass, and we said back here, the more mass an object has, the more inertia the object has. So if it has a higher mass, it's going to move more quickly. Going all the way back to Physics of Science 10, what is the formula for kinetic energy? Do you remember? EK is equal to EK and EP become very crucial in physics. Remember when you learned about the pendulum swinging? EK is equal to 1/2 mv squared. These two have a relationship. If I increase the mass, EK is going to go up. If I increase the velocity, EK is going to go up exponentially. So as I increase the mass, the gun is going to move further backwards at a much more quick pace. What about this one here? Why, when a person on a skateboard pushes on the way, the person accelerates in one direction? What? Oh, when you're pushing off of a wall on a skateboard. That's what this image is here. And then there's a wall here. When you push off of a wall to get going, why doesn't the wall experience any acceleration? It has a fixed point. It's not moving. And the force that it's giving back is going to be, even though the force of the skater is equal to the force of the wall, it's not fluid. That's just like, Daniel, hop up and push on my counter this way. With everything you've got. Push on the higher end so it's easier for you to push on. Push with all you got. Okay? Okay. The counter is fixed to the floor and it's pushing back against Daniel. But it has the larger mass. This whole counter system and everything inside of it has a mass larger than Daniel does. So when I say that the force of Daniel is equal to the negative force of the counter, how do I solve for force? What's the formula for force? So this is the mass of Daniel times the acceleration of Daniel is equal to the mass of the counter times the acceleration of the counter. This mass is quite a bit larger, and so the acceleration will be lower, whereas Daniel's mass will be little, but its acceleration will be larger, and so the forces are equal. This acceleration was next to none. I mean, the counter did move, so there was a little bit of acceleration there, but it was negligible. So it was all of Daniel against all of the counter. Do you see the relationship between mass and acceleration of Daniel versus mass and acceleration of the counter? The counter pushed back. And it's not a living thing, and it doesn't have hands, and it wasn't this big tug of war. I mean, we could set Daniel up against Rainiel here in between. Lock your fingers together and push on each other. Move each other. You have to move each other the length of the table. Start in the middle of the table, and whoever reaches the end. We're going to look at practice problems 74, 12, and 13, and then these practice problems here that I wrote on the back sheet of, but 1, 2, and 3. Okay?